This video is about how to do infinite damage in Dungeons & Dragons. Kinda. In truth, I'll be talking about a sort of house rule in the game Dungeons & Dragons that plunged me into a surprising mathematical rabbit hole into probability and infinite series. If you're from the math side of YouTube, I hope this may teach you a bit about random variables, expected values, and the tip of the infinite series iceberg if you're unfamiliar with these topics, and have you appreciate some of the unexpected mathematics in these games. And if you're from the D&D side of YouTube, I hope this inspires you to incorporate this super interesting dice rule into your own homebrew. I sure have. Or maybe you learn how to play D&D a little smarter too. Anyhow, here's my video on the dice rule with infinite potential, exploding dice. Now, before we begin, I should state that exploding dice is more of a house rule, or homebrew, in Dungeons & Dragons 5th edition, and is more native to other TTRPGs. Regardless, this video will still discuss its use in D&D rather than in other TTRPGs, because D&D is sadly the only one I'm familiar with. And for those who are unfamiliar with D&D, know that you won't need any prior knowledge on the game for this video, and I'll try my best to explain any game jargon as needed. For instance, throughout this video, I'll be using a dice notation common in TTRPGs. When seeing a D followed up by a number, this refers to a dice of that number of sides. If a number precedes the D, then that tells us how many of that dice is rolled. For example, 3d12 plus 4 refers to the result of rolling 3 12-sided dice and adding 4 to get the final result. In D&D, we commonly use the d4, the d6, d8, d10, and 12 to roll for damage. We do use other dice for other uses, such as the d20 and the percentile dice, but they're not really used for damage or exploding dice in D&D, so we won't really talk about them in this video. So what are exploding dice? Well, in D&D, it's an alternate, more exciting way to calculate damage. Basically, when you roll exploding dice rather than normal dice, if a dice rolls its highest possible value, for example a 6 on a d6, a 10 on a d10, it explodes, and you can roll an additional dice of that size and add it to the total sum. Moreover, this can chain, as the dice resulting from the initial explosion can also explode if they roll their highest possible value, and so can their resulting dice. Ultimately, there's no upper bounds to how high these dice can roll, thus this rule's infinite potential. And due to this infinite potential, if my Dungeon Master gave my level 8 rogue a magic light crossbow that uses the exploding dice rule to calculate damage, my level 8 rogue can go from dealing around 10 damage normally in one attack to possibly dealing 106 damage in only one attack. Heck, I could one-hit kill a Tarask if I'm lucky enough. Though I should state I need to be very lucky for this to happen. Remember, an exploding dice only explodes if their highest value is rolled. Thus, 87.5% of the time, my rogue will still be dealing around 10 damage, and I'd be considered lucky if it explodes even once. And the probability of exploding even once gets slimmer for larger dice. D4s have a 25% chance of exploding, while D12s have an 8% chance of exploding. 1/3 of a D4's chance. This brings up a major concern some players may have over exploding dice, how it may disrupt power levels between different dice sizes. This may be a bit of an assumption on my side, but D&D seems to be designed with the thought that larger dice are supposed to be stronger than smaller dice. A d6 should roll higher than a d4. A d8 should tend to roll higher than both, and so on. And some features in D&D are designed with this in mind. However, since with exploding dice, smaller dice explode more often, introducing exploding dice into your game seems to possibly disrupt some of these game design choices in D&D. For example, in D&D, a hand crossbow is a one-handed weapon that calculates damage using a d6. In terms of damage, it's weaker than its cousin, the heavy crossbow, that calculates damage using a d10, but requires 2 hands to use. Between these two weapons, having an extra hand to do other things in battle comes at the cost of less damage per attack. However, if you make both weapons magically use exploding dice to calculate damage, since the d6 explodes more often than the d10, is the hand crossbow now more powerful than the heavy crossbow? If so, then why use the heavy crossbow at all when the hand crossbow only uses one hand and can deal similar, if not more, damage? For another in-game example, at 16th level, a monk calculates the damage of their unarmed strikes, or their punches, using a d8. Then, let's say that the same monk levels up to 17th level, where their unarmed strikes get an upgrade and now use a d10. Now, let's say that for some reason, the monk can use exploding dice to calculate the damage of their unarmed strikes. Maybe their DM gave them a cool magical homebrew items to do that. If a d8 can deal more damage than d10s when exploding, since they explode more often, then wouldn't that mean that the monk became weaker upon leveling up? To actually figure out how truly powerful exploding dice can be and how each exploding dice size compares with each other, our best bet is to calculate the average result of each exploding dice. However, how do we go at calculating the average of something like exploding dice, especially with its infinite potential? The first way I thought to analyze the average was to simply simulate thousands of exploding dice rolls through Python and estimate the averages for each exploding dice size that way. For those interested, here are the results of my simulations. However, I wasn't satisfied with finding a close estimate, and much rather wanted to find an exact formula to calculate these averages. And to achieve this, we're going to have to take a detour through both probability and calculus, with random variables and infinite series. As a refresher, or maybe an introduction to some, a random variable, usually denoted with a capital letter, is like a function that takes in the possible outcomes of a random event or process and associates each of them with a numerical value. In this example, the random event is flipping 2 coins, and the values are the number of heads from the outcome. Some other examples of random events and values include betting on a game of chance and the net profit it made, and of course, rolling some dice and their result. The probability distribution of a random variable is like another function that takes these values and tells us the probability that each value occurs. The average, or the expected value, of a random variable is derived from this probability distribution. It's calculated as the sum of all the possible values multiplied by their respective probabilities. It's somewhat like a weighted average, where values with larger probabilities are given more weight. The expected value can tell us what to expect in the long run of a repeated random event. In a gambling game, if the expected value is positive, then you can expect to make a profit after many rounds. This is why casino games tend to be designed with a negative expected value. However, we can also compare expected values of different random variables together. For another D&D example, if you're comparing spells, then the one whose dice has the higher expected value will tend to do more damage than the other in the long run. Overall, the expected value is a valuable measure for decision-making in random events such as these, and is perfect to measure the power of exploding dice. So that's great, we just have to define a random variable as the result of an exploding dice and find its expected value. So what would this random variable look like? Well, if this is what a usual d6 probability distribution looks like, then this is what an exploding d6 distribution looks like. Oh. Okay, so there's a lot that stands out with this distribution. For one, there are a bunch of gaps occurring at every multiple of 6, which is kind of odd until you realize that it's impossible for an exploding dice to result in a multiple of its dice sides. After all, if an exploding dice chain totals up to a multiple of the dice's sides, then that means all of the dice in the chain rolled their highest, including the last dice of the chain, meaning the dice chain can't end there. Thus, an exploding dice chain can only stop once their sum hits a non-multiple of the dice's sides. Another point of interest is that each probability seems to always equal 1 over a power of 6. To explain this, let's look at how we derive the probability of one such case. The probability of rolling a 15 with an exploding d6 would be the probability of rolling a 6 on the first roll, rolling a 6 on the second roll, and rolling a 3 on the third roll, ending the chain. Thus, the probability of rolling a 15 with an exploding dice would be 1 6 times 1 6 times 1 6, or 1 over 6 to the third. For any result of an exploding dice, their probability should equal 1 over s to the n, where n is the number of dice required to roll as high as this result. This was how I was able to calculate some of the probabilities from earlier. Given that my rogue's exploding dice crossbow did an exploding 1d8 plus 6 damage, it should take an exploding chain of 12 eighths ending with a 4 to deal exactly 106 damage, meaning a probability of 1 over 8 to the 13. And a chain of 83 eighths ending with a 6 to deal exactly 676 damage, the full health of a Tarrasque, with a probability of 1 over 8 to the 84th. But the most important, and I guess you can say infinitely big, point of interest is that the distribution appears to be infinite. And, well, of course it is. Since there's no cap to how many times an exploding dice can chain, there's an infinite number of values an exploding dice can land on. So even if we have the probability of every value, we're going to need to find the sum of an infinite number of terms to calculate the expected value. Of course, we could just add each term one at a time and see what it looks to converge to, but to find a formula, we'll have to look at the concept commonly taught in calculus, infinite series. What infinite series teaches us is that sums of infinite terms can add up to normal finite numbers, but only if the sum's terms shrink fast enough. The infinite series that do sum up to a finite number are said to converge, while those that don't are said to diverge. And our expected value sum happens to be a convergent one, though that may not be apparent in the form it is in now. Now, I won't go very in-depth about the derivation process, but I'll explain some of the more cryptic parts. For example, here you may ask why I simplified this sum from 1 to 5 down to a weird fraction instead of simply 15, or why I unsimplified what was previously 30 to 6 times 5. This is because if we follow the same steps to find the expected values of other exploding dice, we'd find that they'd match up with the current form that we have here. Therefore, we could just smush them together in order to get an expected value formula in a generalized form for exploding dice of any number of sides. From here, we can split our sum into two different sums using sum summation rules, and by doing this, we've split our series into two easier to solve series that we'll now look at separately. The first one is a specific type of infinite series called a geometric series, identifiable by how each term equals the previous term, but multiplied by some common ratio. In this case, 1 over s. It's kind of similar to that conversion series shown earlier, where that one's common ratio was 1/2. We can calculate what an infinite geometric series sums up to using this formula, where a equals the first term of the series and r equals the common ratio, but only if the absolute value of r is less than 1. After plugging in our first term of the series and 1s as our common ratio, and doing some simplification, we ultimately get that our sum equals s over 2. So that solves the first series, but what about the second? Well, we can once again use the geometric series formula, but only after some manipulation. In the end, we get s over s minus 1 from the second sum. Now we can just simply add these two results together, and we get this. And this is it. This is the formula we can use to find the exact expected value for exploding dice of any number of sides. And this formula does seem to match up with the simulation results. So what can we say about the power of each exploding dice in comparison to each other? Are larger dice still more powerful? Yes, but mostly in larger cases. In the case of single rolls, one can certainly make the case that exploding dice of a certain size may be slightly better than the dice of a size larger. An exploding d6 actually rolls results of 8 or higher at a slightly larger probability than normal or exploding d8s. It's the same between d4s and d6s, d8s and d10s, and d10s and d12s. However, over many rolls, the power of averages starts to show, and the dice with higher averages will start showing higher results. Throughout an entire campaign where you're likely to throw dozens of attacks, heavy crossbows will still likely deal more damage than hand crossbows, and level 17 monks will still punch harder than level 16 monks, even under exploding dice. So that's fantastic! We can bring in exploding dice into our campaigns without disrupting the game's mechanics. I personally think it's a very interesting and exciting way to reward players by boosting their damage. Although, with these averages, it doesn't look like I'll be insta-killing Tarrasques anytime soon.